Unit vectors. Unit vectors have a magnitude of 1. Their sole purpose is to indicate a direction in space. In the Cartesian coordinate system, we use I to describe the x direction and j to describe the y direction. If I were to describe vector A in components using this system, it would be equal to a sub x I plus a sub y j. Products of vectors. The scalar product is called the dot product. It is indicated by vector A dot vector B. To calculate it, you take the magnitudes of both vectors, multiply them, by the angle between the vectors when they are placed tail to tail. The dot product, vector A dot B, is equal to A times B cosine theta. It is also equal to B times A cosine theta. It is important to note that the dot product is a scalar quantity. However, it may be negative, positive, or zero, depending upon the angle between the two vectors. We can also use components to calculate the scalar product. You do so in the following manner. The scalar product of A dot B is A sub x times B sub x plus A sub y times B sub y. Once you have this value, it is a simple matter to solve for the angle between them. Cosine theta is going to be equal to the value that you got by the above manner divided by the magnitude of A times B. The vector product of two vectors is called the cross product. To calculate it, we use C equals AB sine theta, where C is the magnitude of the cross product. A and B are the magnitudes of vector A and B, and theta is the angle between vectors A and B. You will get the direction with the right-hand rule. To determine the direction, you can either use the right-hand rule or the screw rule. The right-hand rule says if I am to determine the direction of A cross B, I place my fingers along the direction of A with my palm facing B, curl the fingers, and whichever way my thumb points is the direction of the vector. In this case, my thumb points into the page. You can also use the screw rule, which says move the first vector towards the second, and whichever way that would screw would be the direction of the vector. In this case, it would screw into the page. Here's an example of how to calculate the cross product using the components. In this example, we are calculating the cross product of two three-dimensional vectors. Of course, you could use this method to calculate the cross product of a two-dimensional vector, noting that one of the dimensions would be 0.